Okay. So I think this is the finish of this POVN. And before we go on, let me just uh do some like terminology or basically a very small recap. Okay. So this is just recap of this bracket notation because we are going to talk about Bell inequality and some results, some like weird thing. So it's just a small recap. So 0 and just 1 0. So this is very simple. 1 0 1 and the plus is just so sometimes sometimes people will just write plus or minus to be 1 over square root of 2, 0 plus or minus 1. Okay, so this is just simple. And these are like eigenbases of z, and these are eigenbases of x. But okay, so sometimes that these 0 and 1 are people are called computational basis. So this is the some terminology called computational basis. And these are called diagonal basis. Okay, good. So just a small recap, right? So let's say if I take a plot states, if I use the computational basis to measure plot states, then I will get either 0, I will get either 1 or minus 1. So remember, this is 1, this is minus 1. This is eigenvalue 1. This is eigenvector corresponding to eigenvalue 1 of z, and this is eigenvector corresponding to eigenvalue minus 1 of z, right? So if I start with either plus, then I will probability have to get the 0, probability have to get 1 if I use z basis. So this is the weird thing of quantum mechanics. If I use the correct basis, so let's say if someone gives me plus states, if I use the correct basis, meaning that I use x basis, then I will get 1. If I use the wrong basis, I use z basis, then I will get probability half to either z 1 or minus 1. Okay, so this is just very let me just write down, right? So this is the power of quantum mechanics. If you use the correct basis, then you are good. You get correct 100%. And if you use the wrong basis, then you get nothing, right? Because you do wrong basis, then you get 1 or minus 1 with half. Then it's the same as you flip a coin. There's no extra information. Okay, good. Okay, so let me just talk about small applications of this POVM. This is very simple. This is very simple called the superdense coding. So let me just write down super dense coding. Oh, by the way, all this material that what with high probability that you can find out in the textbook. No. So this superdense coding just say that okay, so let me just write. So one can use in Bell state. Okay, so from now on and next week we will spend lots of time talking about this Bell state. So one can use Bell state. So remember, I will tell you that a very weird thing about this Bell state, and it's not on Sakura textbook, so it's much weird results. So one can use this Bell state. Let's say Alice and Bob, right? And then they share a Bell state. So this side just be this. And Alice can so if Alice and Bob share this Bell state, right? Side. And Alice can use 1 qubit to transmit two classical bit to Bob. Okay, so let me explain. So we will give a small protocol such that Alice can just send 1 qubit to Bob, but this 1 qubit can transmit the 2 classical bit information. And oh, by the way, so there's a let me just say something. So if you go so some people will say this. So some people will say that if I give you a state psi, let's say single qubit, A0 plus B1, right? This is a single qubit. And some people will say that this state psi can store arbitrary large information because these A and B are like arbitrary. These A and B are complex number, right? So and they are continuous. So somehow like this one qubit should store like infinite information because I can store arbitrary like classical bit into some like binary representation of real number sh, right? And so this seems that one qubit can store like arbitrary large amount of classical qubit, and this is somehow like the misunderstanding, right? So this is not true. There are a few reasons. The first reason is that you need to measure, right? So if you measure these states, then state will disappear either 0 or 1 if you use a standard basis. And actually, that one can prove that more stronger results is that one qubit can only transmit like 2 qubit information. And there's a theorem that I will not talk about proof, but this super dense coding is basically the best. So if I can send one qubit to you, then this one qubit information can only store at most 2 classical bit information via this spell state. Okay, so let me just quickly say how to do this. This is trivial. So it's simple, right? So the starting point is that Alice and Bob then share a Bell states, either 1 or square root 2, 0, 0 plus 1, 1. So if Alice want to send 0, 0 to Bob, then Alice just do nothing to the state. Okay. And if Alice want to send 0, 1 to Bob, then Alice just take the X. Oh, sorry, let's say take Z. By the way, so when I say Alice and Bob share Bell states, meaning that Alice can do arbitrary unitary on her side. So her unitary can only affect the first qubit, right? So it's basically entangled, but Alice has no way to affect the second qubit. Okay. So if so this Z actually is Z1. So this Z meaning that Alice can do a Z qubit, can do Z operation, do Z rotation. So remember that polymetrics are all unitary, right? So we can do Z rotation. And if Alice wants to send 1, 0, then you just do let's say X. And if 1, 1, then Alice just do some I1. Yeah, so these are all unitary. Okay, so let's write down. So if the 0, 0 state is basically this, it's the same, right? So this is what about Z, right? Only act on this, right? So let me just provide I forget about to say this one. I will not write this again. So basically, remember that this is Z and then Q2 -1. Okay, good. And X is plus or minus, which is plus or minus, so minus. So these are things that right. So if you take Z, then 0 is 0, right? So it's 0, 0 minus 1, 1. And then remember that X is a 3-3, right? So X on 0 is basically 1, and X on 1 is 0. So remember that X is a 3-3. Or basically you can use just some NOT gate. Wait a sec. Okay, so if good. Right, so 1, right? So how about X? 1 over square root of 2. X on 0 is flip, right? So it's 1, 0 minus, sorry, plus 0, 1. Flip, right? and IY you can check by yourself. So IY, so Y is just IXZ. This is a simple. So you just need to remember X, you just remember Z and X is briefly, and Y just by definition just I times X. So Y is just basically I times XZ. Okay, and so it's 1 over square root of 2. That's 0, 1 minus 1, 0. So why I need to do why I'm talking about this calculation. Oh, by the way, so remember that the second qubit is in attack, right? So see, second qubit is fine. That oh, by the way, it's just so notation there. Okay, so what I'm saying is that so this is the protocol. So the protocol first is that Alice and Bob they share a Bell state. And if Alice wants to transmit 0, 0, then just do nothing. If it's 0, 1, is just do Z, and 1, 0, just do X, 1, 1, just do IY. And after this, Alice just send this qubit to Bob. So let me just write down. So Alice just send her qubit to Bob. Okay, so now imagine that all these 4 states are all these 2 qubits are go to Bob, right? Go to Bob. So there's a one property that hopefully is easy to see, that these 4 states are orthogonal to each other. So these two, right? So these two are orthogonal, right? 1 and minus 1, and this and the X, let's say 1, 2, 3, 4. Let me just do a simple calculation. So 1, 2 are orthogonal because 0, 0 plus 1, 1, 0, 0 minus 1, 1, right? And the 1, 3 are orthogonal because 1, 3 doesn't, because 3 doesn't have 0 and 1, 1. 3 is at 1, 0 and 0, 1. And the 1, 4 are orthogonal, same reason. And the 2, 3 are orthogonal. 0, 0 minus 1, 1 is, there's no 0, 0, 1, 1. And the 2, 4 are orthogonal, right? 0, 0 minus 1, 1, there's nothing. And the 3, 4 are orthogonal because this is either plus, this is minus. So these 4 different states are orthogonal, right? So by definition, by the previous results, that Bob can do one measurement and 100% know which state it is, right? But because these 4 states are also known. So remember the previous state distinguished theorem tell me that if 4 states are orthogonal, Bob can do 100% correctly know which state it is. So what? So Bob, so let me just write down. So Bob knows which state it is 100%. Right? So this means that if there's a, so this finishes the protocol. This is true. So this protocol just tell you that if Alice and Bob first share a Bell state, and Alice wants to transmit 2 classical bit information to Bob, then the second step is that Alice just follow this rule. Alice just say, if I want to transmit 0, 1, I just take Z. If it 1, 0, I take X. If 1, 1, I take Y. And after that, I just send this state to Bob. And by definition, Alice and Bob gets 4 possible outcomes. But by the previous theorem, that these 4 states are orthogonal to each other. So Bob can do it 100% to get which state it is. So Bob will receive 2-bit information. So this is the results. So we show that Alice can use 1 qubit to transmit 2 classical bits to Bob. Okay. Oh, and I want to say one thing. So it's necessary. Oh, by the way, so let me just say a thing. So I think everyone knows about this, but so the Bell state, right? The single Bell state. So right. So if Alice, let's say we forget about this super dense coding. Let's say if Alice do the Z measurement on her qubits, right? So it's so this if you doesn't familiar, you can imagine that Alice do this kind of projectors. So Alice do measurement on her qubits, then with probability half, right? Because they are equal weight, with probability half, then Alice will get 0 qubits on her side, 0, 0. And the state will collapse to 0, 0. Or probability half, the state will collapse to 1, 1. So that means that there's a non-trivial correlation between Alice and Bob, right? It's either Alice can, if Alice use Z basis to measure, she has probability half to get 0 on her sides. But Bob, the non-trivial correlation will force Bob to get 0. And the things, but so this means that there's no way that Alice can so Alice cannot convey her message to Bob without sending a qubit. The reason is that if Alice want to tell Bob that, oh, this is I want to send 0 to Bob, and there's no way, right? Because I use once I measure that, I get probability half. Okay. Let me just so there's a non-trivial correlation. And okay, so by the way, this non-trivial correlation, people will say that this is somehow like a quantum entanglement, right? Because either like two of them must have the same outcome. But this is not actually not a whole quantum entanglement story. This is just class. Actually, this 0, 0, 1, 1 can use a classical analogy. So actually, this is not quantum entanglement. The reason is that I can consider a classical case that there's someone just put 2 balls into this box, and someone says that these two balls have the same colors. Either they are all black or they are all white. Right, so it's either all black or either it's all white. And let's say you're Alice, right? And you just put your hand into this bag and you take 1 ball out. And if this ball is black, then the rest must be black, right? And if you get white, then the rest of this ball must be black. So then this is the same as the probability half. You get both. You get a box which is all 0, and then you get a probability half. You get a box is all 1, right? So this is not a true entanglement story. And the true entanglement story is that this psi you can write as 1. You can also write as plus plus and minus minus. I think I have shown this before. So this is actually the weird part. The weird part is that even if Alice uses X basis to measure, then Bob will always get the correct X basis correlation. And if Alice use minus minus, then Bob will always get minus minus correlation. This change of basis results from this X and Z cannot be described by using this classical ball analogy. So if you don't allow the quantum mechanics to do X and Z rotation, but only allow like one like X, let's say I define my quantum information, say you are not allowed to do X, right? You are not allowed to change basis. Then this half of this correlation can be like translated into classical one, just use this ball analogy. But if we change the basis, then we will see something, some weird outcome. Okay, so this somehow like finish this section. Any question? So I try to do Bell inequality. But before we do Bell inequality, maybe we can do some interesting stuff with Hamilton. Okay. Let's do some interesting stuff, and we go back to do Bell inequality. So let me just talk us this. This is different from all the quantum mechanics you learn, and this is called uh oh by the way, have you guys know about Bell inequality, or you never heard about it? All right, that's fine. Let me just talk about Bell inequality. So there are two ways to talk about Bell inequality. I will first use the standard way, and then in the next week, we will use like more like computer science way. Uh, let me just do this. Okay, so this is Bell inequality. This is famous due to several reasons, but one reason is you got Nobel Prize and show that entanglement is a really true thing one can measure. So let me just see how I can do this. Okay. So the situation is this. Okay, this is Alice and Bob. Okay, and let me just do this. And then let's say they share some state psi, which is Bell state. Or maybe okay, so Alice and Bob, they are separated very far. And let's say Alice can do either two kind of can use two kind of measurement. One is A0, one is A1. So let me just I will explain this what the hell is going on. And Bob has B0 and B1. So this A0 will just be some measurement, or you can imagine it's POV, but let's say A0 is some measurement which is square equals to 1, and there are permission. Also true for Bob. Okay. So this just means that Alice have to. So Alice and Bob, let's say they will get some information from third party, and Alice can do so Alice can use A0 to do measurement, or Alice can use A1 to do measurement, and then Bob can use B0 or B1. So they are like very happy. So from Alice and Bob, each of them can choose two kinds of measurement. So for example, you can imagine that Alice can choose A0 to be Z basis, and Alice can use A1 to be X basis. And Bob can also do B0 to be X basis, or B1 to be Z basis, or arbitrary, or even their combination. So for example, let's say Alice can also use, let's say, X plus Z divided by square root of 2. By the way, it's easy to check that this square is 1. So it's half of X squared plus Z squared plus XZ and ZX. And then notice that Pauli matrix is anti-commute. This is 0. So it's 1 because X squared and Z squared is 1. So what it means, this is very general scenario. Alice have two kind of bases you can do, and Bob also has two kind of bases. Okay, but no matter what, after let's say Alice use A0 to measure this, to do anything, right? She will always get either plus or minus 1 outcome by the axiom, right? Because we say that A0 square is 1. So if Alice choose to use A0 to measure, then she always get either plus or minus outcome by eigenvalue, and also for Bob. Okay. So no matter what Alice and Bob do, that after their measurement, all the measurement outcome will this A0, B0, A1, and the B1 will always give us the plus or minus outcome, right? By definition. Okay. So, and also that this A0 or A1 are on from Alice's side, and the B0 and B1 are from Bob's side, right? So must be a simple commutation relation such as AI or BJ are all commute for I equals to 0 and 1, and the J equals to 0. Good. 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 Okay. Okay, so let me just talk about Bell inequality. So let's say there's no okay, let me just write. So this is Bell expression. Actually, there are a lot of names. So it's A0 B0 plus A0 B1 plus A1 B0 minus A1 B1. So this is the standard textbook way to express Bell expression, right? Let's see. So if there's no quantum states, if there's no entanglement or no others, there's no quantum state that between Alice and Bob, then it's easy to prove that. Let me just write down, right? So let me just, so if there's no quantum, then this Bell expression, or you take any expectation value is basically, let's say this is L. It's it's almost 2. Actually, it's either 2 or minus, but let's say. So one can write A0 plus B0. Yeah, it plus B1. And then A0, either B0 minus B1. Right. And since that each of by B0 and B1 are plus or minus 1. Right. So one of the B0 plus B1 or B0 minus B1 must be 0. Because B0 and B1 belongs to plus or minus 1. Right. So without loss of generosity, I can say this guy is 0. So this is basically square, it's either like 2 or minus 2. Okay. So the absolute value of L is either like less or equal to 2. Okay, so this is a standard, like if there's no quantum or any so-called non-trivial correlation or whatever, you always get this 2 or minus. Or simply speaking, if you forget about all this like expression, if you start with these 4 equations, you forget about all the quantum mechanics or whatever. You just see these 4 equations. And notice that I'm not saying that this A0, A1, A2, B0, B1. I'm not saying that these are like 2 by 2 matrices. Whenever all these matrices, whenever like this A0, A1, B0, B1, there are like arbitrary large matrices, I can define this Bell inequality, right? But especially when A0, B0, and if they are all just one number, then it's basically less or equal to 2. Okay. So this is the standard. Okay. So this is the so-called classical region. Okay, so for the quantum, that this is, I think everyone knows about this. Okay, so it's that let's say there is a state psi, which is this. I think I can do this. And let's say if Alice choose X to be a Z and A1 to be either X. I mean, hopefully I didn't, let's say B0 is either X plus Z divided by square root of 2. And the B1 is, let's say, Z minus X divided by square root of 2. And it's easy to check that, as I say, that these are all square root of 1, and these are all Hermitian. And one can calculate this. One can calculate this guy. This A0 one can calculate this A0, B0 by just using this definition. Okay. And let's do this. Wait. So did it? So let's do this. Good. So everyone knows about what I'm doing. So let's imagine that there's a state psi here between Alice and Bob, and Alice choose these two measurements, and Bob choose these two measurements, and there are valid square equals to 1, and there are dimensions. So there are valid like operator projective measurements for each one. Okay, so we can calculate this guy, right? So let me just wait. So let's see. Okay, so let me just try to, so let me just write as this way. Okay, so this is Z. This Z is X on the first qubit, X on the second qubit, and the Z on the first qubit, second qubit. And notice that these are relational. So ZX, right? When Z X on X, then this X will be flipped, right? Become 0, 1, and 1, 0. So actually, there's no contribution for this term. But there's a ZZ term, right? So ZZ, there's a ZZ term. So ZZ icon is 1. Good. So let me just write it. Maybe let me just do it slowly. So let me just do it slowly. All right, so we just calculate this. So ZX, what is ZX? It's 0 and 1 plus ZX icon is 1, 1, right? So it's -1, 1, and 0 plus 0, 0, minus 1, 1. Sorry, plus 1, 1, right? Because each of these will give you -1. So 2, 0 will give you, so 0, 0 plus 1, 1 inner product with 0, 0 plus 1, 1, right? So it gives you 2. And then remember, but there's a square root of 2, right? So it's basically half times half, 1 over square root of 2. This and this will give you x2, right? And there's a 1 over square root of 2 here, and that's half here. Okay, so A0 and B0 will just give me 1 over square root of 2. Good. Hopefully it's just, oh, sorry. Well, I will do it carefully, but hopefully it's understandable. Okay, so let me just, so everyone knows how to do the calculation. So I will do it faster. Okay, so how about like A0 and B1? Okay, so remember that, so A0 and B1 is the same, right? It gives you ZZ, right? And the ZX term will be canceled, right? There's no ZX term, so this is 1 over square root of 2. Same reason, okay? And A1 and B0 is basically X squared, X and X, and the X and same is the same. So let's check this. So this say psi is 1 over square root of 2. 0, 0 plus 1, 1. So if we do x side, so remember x is a flip, right? So 0 flip to 1, so it's 1, 1 and 0, 0. So it's the same as original state. Okay. So if we do A1 and B0, we get XX plus XZ, and XZ is 0, right? So it only survives XXX, so it's 1 over square root of 2. And for A1 and B1, there's a extra minus term, minus XX. So it's A1 minus B1. A1 B1 is 1 minus 1 divided by square root of 2. Okay. So if we write down the this Bell expression, if we act on this Bell state, then it's basically 1 over square root of 2 plus 1 over square root of 2 plus 1 over square root of 2 minus 1 square root of 2, which is 2 square root of 2. Okay. So it's greater than 2. Okay, so this means that if there's a state psi between Alice and Bob, then Alice and Bob can do a measurement, do some weird correlation measurement, which try to compute this number. So in the next week, that I will try to give like one interesting quantum game called CHSH game to basically give an interpretation of this number. So next week I can interpret this expression as the probability. Okay, so this is 2 square root of 2. So if there's no states between quantum state between Alice and Bob, then whether there's no extra correlation between them, they can get 2. Okay, so there's an interesting question, right? So in classical, then this guy is 2, right? It's less equal to 2. In quantum, we say that Bell state can arrive the 2 square root of 2, right? So now, so one open question, right? So this is a question that can we do better? So can we do better? Meaning that maybe if Alice and Bob they share more exotic states. Let's say they share like 100-dimensional quantum state, which is not like Bell state, and then they try to do the calculation. Can Alice and Bob get more exotic one, more large number? Okay, so the trivially, so let's say trivial. So what's the upper bound of this L? This is expression, right? So these are all like Hermitian operator square equals to 1. So the trivial upper bound will be 1, 1, 1, and minus 1, right? Because A0 square is 1, B0 square is 1, and all numbers, all the matrices or operator here square is 1. So the trivial bound is 4. And the question is that whether we can find we can find some state which arrive this or get the higher than these 2 square root of 2. And in the quantum, in this is much weird. This is much more difficult. And this is, in general, this is called Stirner's bound. Stirner's bound. So Stirner's bound meaning that, let's say, you consider more general parties and you write down arbitrary Bell expression. And my question is that what's the maximum value you can violate to get? So let me just tell you the answer. So for Bell inequality, I think everyone knows, right? So the answer for Bell inequality is that no, right? So the 2 square root of 2 is the best. And okay, so we have 17 minutes. So I can try to prove this, but I think this score is not easy to write. So I will write here. Okay, so final 17 minutes, we'll prove that 2 square root of 2 is the best. I will try to do this. I think because this kind of proof that you can find out online everywhere. And then actually there are two kinds of it. But I will just use the stupid way so that you understand. So that I will just take a picture of this. So there's no you don't need because I think this is much difficult to write. Okay, so let's do this, right? And so remember that if you forget, you can so all these are matrices. You can imagine that they are all matrices, and they are all commutes. There are two different parties, right? So they are connected with each other. And I'm not saying that these are 2 by 2 matrices, right? I'm allowing that this AJ to be arbitrary D by D matrices. So for arbitrary N by N matrices. As long as they are Hermitian and they are all Hermitian. And say they are all Hermitian, and they are all Hermitian, and they satisfy all this. So the states between X and Y can be arbitrarily large. So state psi can be just arbitrary D by D convex sum. And I'm claiming that this guy is at most square root. Is everyone good for a statement? So now everything becomes some simple mathematical equation. Someone trying to. Okay, so the standard proof is that you just write this. You just write this guy. Let's call this N. L. And I combine this I write as this B0 plus B1 plus B1, B0 minus B1. And I just square it. Square is a matrix, right? So this term square, right? So this term square is A0 and this term square, and then A and B are commutes. So A0 square is 1, right? So actually I got B0 plus B1 square. Okay, and this term is also the same thing. But there's a commutation. There's a commutation of this guy and this guy. So this times this is A0. So notice that all the key calculation idea is that A and B are commutes, right? But B doesn't commute itself. And A also doesn't commute itself, right? So you get B0, 0, 1 plus A1, A0, B0 minus 1. B0 plus. A1 and A0 and B0 minus B1 plus B1 to get this. And then remember that you need to make sure that A0 and A1 B0. You need to make sure that there are the correct order. 0, this, and this, and this. Okay, good. And don't worry about this. So B0 squared and B1 squared are 1. Right? So this and this, and then there are commutation. Their cross term will be 0 because this is B0 B1 B1 B0 and B0 B1 B1 B0. So what will I get? I get 4. Right? I get 4. Is it? Right? I get 4. Right. And about this, that I can just write out. So I get A0 A1. So this one I get B0 squared. B0 squared is 1, right? Minus B1 squared. I mean I can finish this. Minus B1 squared. So we get B0 minus B0 B1 plus B1 B0. And similar for this term. So this term B0 B1 minus B1. Okay, so now here comes the trick. I can write these guys commutation, B0 and B1. And this term is also commutated, B0 and B1. Right, so this term is for like, and this term I can write also as a commutator. Right, so I can write as maybe minus, plus A0, A1, B0, B1. So L squared will be just be A, the commutator of A, and the commutator of B times. Okay. So what's the maximum of commutator? What's the maximum of this A0, A1? As a operator norm. Or you take any matrix. What's you take any vector here, right? And what's this? This is 2, right? Because A0 and A1 is at most 1. A1 and A0 is either 1. And there are minus side, but I use triangle inequality. So it's 2. So this guy 2, 2. So L squared is bounded by 4 plus 2 times 2, which is 8. So L is bounded by what? 2 squared root of. So this is and I will explain it in so L is bounded by 2 squared. Okay. Let me just take a here. So so the final thing I want to say is that so what we have shown is that Bell inequality indeed reached the maximum, right? Bell inequality indeed reached the maximum. But what about converse? Let's say you guys play. Let's say you guys try to do the Bell inequality and get two square root of 2. Can you converse it? Can you prove that the middle state must be a Bell state? But this is the converse statement. So we show that 2 square root 2 is the best. But what's the but is it Bell state is the only state which gives you a 2 square root of 2? Or not? Maybe there's some extra like 100 dimensional state which is not Bell state, and they give you a 2 square root of 2. And this is not in Sakura or any quantum mechanics textbook. This is called rigidity. And one can show that you need more mathematical tool, but one can show that Bell state is the unique state which you get 2 square root 2. And yeah, so I will talk about in the future, probably next week. Yeah. So I will post. I will take a picture and upload into the PowerPoint. See you guys.